Wasabi, you guys. Welcome to Integration Bee Training for Advanced. In this section, we'll be learning about Frullani integrals. So, what is a Frullani integral? So, we have a theorem that states that if we have this formation of this integral here, f of a of x minus f of b of x divided by x, and that for some a, b real numbers, okay, and then of course f, as long as the limit for infinity and 0 f of x equals an existing limit. It doesn't have to be positive, but as long as the limits of some function for infinity and 0 exists, right, then this integral here, that's a very bad equal sign, this integral here will always equal to f of infinity minus f of 0 of ln of a over b. Okay, I know it sounds crazy because it's like you're not even integrating, you're just evaluating just based on the function and then coefficients, which is amazing. It's very amazing. So we're going to take advantage of this Frullani integral with certain types of integrals. So that's what we're going to be doing, is we're going to be using this formula a lot. You're just computing f to infinity, computing the limit as x approaches to infinity to the function, and then same for 0, and then the coefficients from a over b. Okay? So let's start with a friendly integral here, just to introduce ourselves to the Frullani formula. We have inverse tangent of x minus inverse tangent of pi over x all over x. Okay, and so of course I see 0 to infinity, I see x, and I see two different functions. Only a function with two different coefficients. And so because of this, we'll go ahead and start using the Frullani integral. And so, let's see, inverse tangent, plug infinity to inverse tangent, we know that's pi over 2. Plug in 0 to inverse tangent, that's 0. And then the coefficients we have is 1 over pi. And so our answer is negative pi over 2 ln of pi. And we're done. That's it. It's as simple as that. That's all you do. You just use the Frullani integral, the Frullani integral formula, right? So super easy. As easy as this can be, it can be a little tricky, depending on what integral you're given. Sometimes you have to format it into a Frullani integral to compute. Okay, so let's dive into some more integrals with the Frullani. Okay, right off the back, this is already looking awkward, right? So it's very tricky. It's, Frullani is it's not always easy to spot. So here, this looks awkward as hell. Like come on, this looks like a divergent integral. But it does converge. Let's see. So we have 0 to infinity. We have 1 over x. Let's try to let u equal 1 over x from our inversion. Ooh. Then what we have is we get sine x minus 1 over pi sine pi x. And then our du, don't forget our du, right? We have x squared. Okay, so what now? Do we just add it like how we usually do, like inversion? No. No, no, no. This is a Frullani. This is a Frullani integral. We have 1 over x. We'll just put that aside for now. And notice that we have sine x over x minus pi over x sine of pi over x. Would you look at that? So what we have here is we have a Frullani integral where our function is sine of x over x. Aha! Alright, let's go ahead and get into that. So if we, here, let me write this in blue. The limit as x approaches to infinity for sine of x over x, this is equal to 0. By squeeze theorem. By squeeze theorem, this is equal to 0. Okay, if you remember your squeeze theorem, right, sine of x is always between -1 and 1. And so dividing everything by x and taking the limit as x approaches to infinity, then this equals to 0, this equals to 0, and because it's between 0, this has to equal to 0. Okay? So by squeeze theorem, this is 0. Minus, if you take the limit as x approaches to 0, sine of x over x. This is a very famous limit. This is equal to 1. Okay, it's a very famous limit. I believe, honestly, I just use L'Hopital's. I'm too lazy to do the geometric proof and all that stuff. Cool, but I like shortcuts. That's just lazy me. So L'Hopital will just get you the answer directly. And so 0 minus 1, and then ln, what are our coefficients? 1 over pi. So our answer is ln of pi. Okay, we have this cool looking function here. What's so suspicious? We have 0 to infinity, and you're probably thinking, oh, I thought it was like inversion or something. But then I saw this x here, and then I see these functions. I see a subtraction sign. This and this function looks very similar to each other. This must be a Frullani integral. Okay, so let's go ahead and dive in. I see that our Frullani integral is, our function seems to be x plus 1 to the power of 1 over x. Okay, so then this must be a Frullani integral. So then if we plug in infinity, let's see, we color this in blue. The limit as x approaches to infinity, we have x plus 1 to the power of 1 over x. Again, whenever we deal with something like this, we use a loophole log. E to the power, say this is technically x plus 1 over x. So we have a limit here. Okay. So now that we have that, we can literally just use L'Hopital's rule. So this is equal to the limit. This is just 1. We just get 1 over x plus 1. And of course, this goes into 0. And so e to the power of 0 is equal to 1. So what we have here is 1. 1 minus, now we solve for x plus 1 over x, the limit as x approaches to 0. Okay. However, I could do a limit substitution. Let u equal 1 over x. Yes, this is allowed. You can do this. Then 0, plug in 0, it's infinity. Okay, and now you have, let me rewrite this as 1, switching this. 1 plus x, x is 1 over u. And now this is u. Ah! Y'all know what this is. Y'all know what this is. This is equal to e. Okay, so now what we have is this limit is equal to e. We have 1 minus e. Okay, and now all we have to do after is just go by coefficients. This is 1 over 2. Okay, so our answer is e minus 1 ln of 2. And this is our answer. Okay? Very simple. It's kind of like we're not really integrating. It's just all you have to do is compute the limit, and that's it. But then again, don't underestimate Frullani integrals. It does get a lot harder. You'd be very surprised. We have 2x squared, we have an x squared, and we have a 3x squared. Interesting. However, there's something sus. We have an x, just a random x there at the bottom, and 0 to infinity. So let's see if we could try to format this into a Frullani integral. Okay, so we have 1 over x. I just want to move that out of the way. Can I format this in terms of Frullani? We have, let's see, 2x squared, 3x squared. This is like e to 2x squared minus 3x squared, so negative x squared. Minus here, we have e to the negative 2x squared. Aha! This is a Frullani integral. Alright, cool. Now we can just go ahead and dive into just computing the answer. So here, if we plug in infinity, this just gives us negative infinity, 0, minus, plug in 0, this is going to give us 1, so we get 0 minus 1, ln of 1 over 2, right? Is that 1 over 2? No, it's not. Okay? Be very careful. Be very, very careful. That is not 2. It's not 2. Okay? If this is x squared and we have 2x squared, we need a coefficient by x, not x squared. So this 2x squared would be square root of 2x. Okay? So our answer would be the square root of 2. And so now our answer here is the ln square root of 2. Or if, for some of you, you guys might want to put it as ln of 2 over 2. Okay, this is our answer. Be very careful with x squares. Okay, you do not want to get eliminated like this. This is the saddest way to get eliminated. So, be very careful. Be very, very careful. Alright, I see we have a rational function here to compute from 0 to infinity. Okay, so I guess it looks like we're doing partial fractions. Or, we don't have to do partial fractions, right? Well, some of you, you might think, oh, this is like Caveman trick. Some function where, I'll call this a dx, some function where f of x is like, I don't know, something like this, like something nastier, then it's kind of, you can't use Caveman trick here. So I guess in this case you can, but just with more complicated rational functions like this, it's a lot nastier. So, but now that I showed you my secret, yes, we're gonna instead do Frullani rather than partial fractions, just because it's a lot faster. So here, 0 to infinity, where I bring out 1 over x, and I get 8 of, let's see, x cubed plus 8 minus 1 over x cubed plus 1. Okay, now, again, it's not the 8, it's the coefficient that we need here. Okay, so in this case, we're going to have to divide by 8. So going to have to divide by 8. This will give us 1x cubed over 8 plus 1 minus 1 over x cubed plus 1 dx. And so now here we can see that our coefficient here is going to be x over 2 or 1/2. Okay, that is a 1/2 coefficient. So now we go ahead and dive into the limit, plug in infinity. You know, this whole function, it's going to be 0. Plug in 0, it's going to be 1. ln of 1/2 divided by 1. And we see that this whole answer is equal to ln of 2. Okay, so just keep an eye on that, right? Instead of doing partial fractions, maybe there's some way where we can factor out an x, and if you can, then that's very good, especially when you have bounds 0 to infinity. Then you could try taking advantage of Frullani. Okay? Whoa. Okay. Do not freak out. Don't freak out. It's a very long integral, but let's see. There's some suspicious stuff happening. We got 0 to infinity x. Okay. And we got some similar functions here. Interesting. So we could probably use Frullani somehow. A lot of these are being squared. What do we do? You're probably thinking, oh wait, well we're having minus and minus. Maybe this like a double Frullani, maybe? We might be having a double Frullani. I don't know, let's check, let's see. And then let's see here. Square root of x squared plus 1. Wait, but we can't compute Frullani. And let me tell you why. The reason why we can't compute Frullani like this is because the limit as x goes to infinity, if our function is just x squared plus 1, this is equal to infinity. So we can't use Frullani, right? We have to use something else. So what do we do? What do we do? Alright, so this is very tricky. It's very tricky. It's probably the trickiest Frullani I've ever made. So here you're gonna have to be very creative. So it's very hard to see. I'm gonna reveal this to you right now so that you have very special awareness of this type of integral. So, well, let me first show you. So we know that this integral, this limit goes to infinity, right? So it does not equal an exact real value, right? However, does this equal to an exact real value? Now you're probably seeing it already like, whoa, we could probably do a 0 substitution, minus x plus x minus x plus x, right? Here, you can easily see that you can just conjugate this limit, x to infinity, right? With x to infinity, we conjugate this, x squared plus 1 plus x, right? X squared plus 1 minus x squared. This just gives us 1 when we conjugate it. And then you can see that when we plug in infinity here, this whole thing just equals to 0, right? And if we plug in 0, well, I mean, if you plug in 0 here, this just gives you 1. Now that we know that, we can apply that to everything here. But wait, let's be careful. Let's be very careful. Can we do that to all functions here? Right? Can we really do that to all functions here? Right? If I'm doing minus x, I would have to do plus x here. Or do I need to do more than that? Right? Because when we conjugate, we have to do, let's see, x plus 4x squared plus 1. But then we get x squared minus 4x squared negative 3x squared minus 1. So this wouldn't really work. This would not work at all. So we cannot just do minus x plus x everywhere, right? Here we need a 2x, then everything converges. And then same applies for the other ones. So pretty much we'll be having to form this into here. As you can see, we need to have kind of like a square root version of each coefficient. Then all of these four limits would converge. As you can see, this would be our f. And then this would be like our f of 2x and 4x and 3x and so on. So how are we going to implement this into here? So that's the tricky part. It's very hard to see, but once I reveal it to you, it's actually not so bad. It's very tricky. So what's going to happen is we're going to be doing a plus x minus x once. Okay, we'll be doing a plus x minus x. Then what's going to happen is here we need like 2x here and x, right? So we're going to be turning this into 2x minus x minus, and then this x here we're going to be using let's see, 4x minus 3x here, which is why the 9 is here instead of here. Aha! So that's what we're going to do. So in that case, when we apply plus x minus x, we get x squared plus 1 minus x plus 2x minus 4x squared plus 1. And then here we get 16x squared plus 1 minus 4x minus 9x squared plus 1. This would be plus 3x all over x. And now we can easily see that this is definitely two Frullani integrals here, right? We have, I'm just gonna, we know what this f is. This is our f here, right? So what we have is we have f of x minus f of 2x here, right? Plus, and then we have our f of 4 of x here minus f of 3x here. Okay, now we can go ahead and solve for f of x, right? The limit we already saw when we plug in infinity, it was 0, and then minus plug in 0, we get 1. And then here, because they're both going to be the same portion here, I'm just it's kind of like factoring it out. So now here we have ln 1 over 2 plus the ln 4 over 3. This is going to give us 4 over 6, which is equal to 2/3. And so our answer is the ln 3/2. this is our answer. Okay, that was very tricky, very sneaky. I wanted to share that with you. A very cool, sneaky trick that may happen. Okay, definitely the sneakiest Frullani integral I've ever made. I'm pretty sure there are a lot crazier ways to hide Frullani. Okay, all right. So that's it. That's our last integral. I hope this was helpful. Definitely rewatch this video and try the integrals yourself so that you can remember the Frullani formula. Okay? Thank you so much for watching, and I'll see you guys in the next part.